Hello everyone and welcome to another video. This time I'm quickly working through the Oxford Math short questions A to E from 2010. I've heard lots of people, I've seen comments anyway, people asking for 2010 and 2015. Cool, I'll try, I'll do my best. I know you've got Matt coming up soon. Like I say, really I'm doing it for selfish reasons as well because it's just handy for me if I've got my solutions to the Matt up on YouTube really. Whenever somebody asks me a question I can say, have you watched the video first, like at school? But yeah, I mean, like to be honest, I quite enjoy doing these questions, so I'll probably start having a go at it if they ask me at school. But it's nice because I've got the answers, down somewhere. I find every time I look at these questions, certain questions anyway, I'll do it in a different way every single time, just because you forget you've done it and you don't really know how you're going to approach it. But yeah. Okay, anyway, let's get on with this. So we've got this line intersecting this parabola and we need the values of k for which the line intersects a parabola. Yeah. Now, this reminds me of when I'm teaching, I sort of often describe, when a line's going to hit a quadratic, three things can happen. Uh, that's supposed to be touching it, or it goes through it twice. In other words, they've got no solution, one solution, or two solutions, just like a quadratic equation itself. And that's because when you set a line equal to a quadratic, you bung it all on one side, make it equal to zero. So you've got another quadratic to solve. And, obviously that should have three possible outcomes corresponding to the three possible geometric configurations, I guess. So this is what we're dealing with here. Anyway, so this one isn't too bad. I'm sure you got this, straight away, kx equals x squared minus 2x plus 1. Set it all equal to 0, x squared minus x times 2 plus k. I think I've got the sign right way around then. And then plus 1. Yeah, minus 2x minus 2k. And that's exactly what I'd have here if I put that on that side. Okay, so now I'm just going to say b squared minus 4ac is greater than or equal to 0 because it's got two solutions. So 2 plus k all squared. I can ignore the negative because I'm going to square it and it will become positive. Minus 4 times 1 times 1, so minus 4 is greater than or equal to 0. So in other words, k squared plus 4k plus 4, take away 4, so just that is greater than or equal to 0. So we get this familiar situation. It's a quadratic inequality. A quick sketch, taking this as the k-axis, it would go through minus 4 and 0. So we're looking for that region and that region. So k is less than or equal to minus 4 or k is greater than or equal to 0. C. Okay, next one. Okay, so straight away, this one just looks like two separate sequences lined up together. The sequence 1, 2, 4, 8, 16, and the sequence 1, a half, a quarter, an eighth, 16th, both of which are geometric. Now, they love arithmetic and geometric sequences in these extension papers. They love them. And other types of sequences as well, and alternating sequences, things like that. They do like sequences. So be aware and, be ready for that kind of question. Now, if we take the first one, you're looking at a sequence which goes like this. I was going to put A there, sorry. 1, 2, 4, 8, 16, etc. Yeah, and we only want n of those terms because they want two n terms of this. So if we sum this to n terms, that should be fine. Now we've got a first term of 1, a common ratio of 2. Now this is geometric, so it's a times 1 minus r to the n over 1 minus r. And that's going to be 1 over, won't bother even writing that down. 1 minus 2 to the power of n over 1 minus 2. Quickly simplifying that, you can see you've got 2 to the n minus 1 because that's just a negative 1 on the bottom. And dividing by negative 1 is the same as timesing by negative 1. And so you get that. For the other one, Sn equals 1, a half, a quarter, an eighth, etc. So same thing here. We've got 1, I won't bother writing that down, but I've got 1 minus a half to the power of n, which is just 1 over 2 to the power of n, over 1 minus a half this time. Now the bottom simplifies to a half, and dividing by a half is the same as doubling. Oh, classic little mistakes which creep in. 2 minus 2 times a half to the n, which is 1 over, well, let's write it as a half to the n. Because when you combine these, you're going to say, okay, so the overall sum is equal to 2 to the n minus 1 plus 2 minus 2 times a half to the n. Okay, so that's 2 to the n plus 1. Right, okay, and then we've got this, like, I'm straight away thinking it's probably this. Just check that this bit equals that. Well, it does, doesn't it? Because that's 2 to the minus 1 to the power of n, so that's 2 to the minus n. So you get 2 to the n plus 1 minus, now that's 2 to the power of 1. If we add these powers, we're going to be doing 1 minus n. So you can have 2 to the power of 1 minus n, and I think that's exactly what it is. So there's B. B is going to be A, I believe. C, what have we got next? This one. Right, I did this completely differently to, when I checked my answers, about an hour ago, I laughed when I saw their way of doing this, which I think is probably better than mine. But this is what I did. I think it's always important to show people. It's also a case of like encouraging people. You can go your own way on these questions. Just because they did it a certain way in a mark scheme, there's no reason you can't do it another way. Just because you didn't see that way, and yes, you agree, it does happen to be simpler. I thought double angle. I suppose, yes, I shouldn't have been thinking double angle because, of course, this paper isn't really written for second year, even of A level. But nonetheless, double angle is really handy here, and I bet you've seen it before, most of you. So that's the same as 1.5 sine 2x. Both sine squared and cos squared can be written as double angle in terms of cos. So cos squared x is going to be the same as 2 cos squared x minus 1. Sorry, cos 2x. Dear oh dear. Cos 2x is the same as 2 cos squared x minus 1. And so you can rearrange that to make it clear that cos squared x is cos 2x plus 1 over 2. And obviously, if you double that, well, you're going to get cos 2x plus 1 over 2. But I might not do that, actually. Similarly, for sine squared x, because it's the same as 1 minus 2 sine squared x, you can say that cos 2x, now let's get this right, 1 minus cos 2x over 2 equals sine squared x. And I can tell it's right because that plus that equals 1. Yeah, good. So, yeah, okay, right. So what have we got here? We've got, to write it all out properly, 1 minus cos 2x over 2 plus 1.5 sine 2x, and then plus a half, well, 1, have I got, yeah. I'm going to write it as 2 cos 2x plus 2 over 2 equals 0. I hope you can see I've just doubled the numerator purely because I've got a common denominator. Then I can see what this simplifies to quickly. Minus cos 2x plus 2 cos 2x is plus cos 2x, and then you've got 1 plus 2, which is 3. So you're going to have cos 2x, if you like, 0.5 cos 2x, as we're loving decimals now, plus 1.5 sine 2x plus 1.5 equals 0. So I can barely read my own handwriting here. 0.5 is that. Okay, so we've got half cos 2x plus 1.5 sine 2x equals 1, plus 1.5 equals 0. This is a typical situation for r cos theta plus alpha. Yeah, I know what you're thinking. You're thinking it's way easier in the mark scheme. Yeah, I agree. Yeah, I saw that as well. They divided through by cos squared and got a lovely little tan equation. I didn't see that. I just genuinely didn't see that. So this is what I did. So I had why am I writing down decimals? What am I doing? A half cos 2x plus 3 over 2 sine 2x equals minus 1.5. I thought to myself, I know I can do this with r cos theta plus alpha. Don't get me wrong, I didn't actually try and solve it. I just thought about it and thought, what am I going to get? Well, your r is going to be this squared plus this squared square rooted. So that's like 9 over 4 plus 1 over 4. That's like 10 over 4. It's root 5 over 2. Yeah, root 2.5. Now, root 2.5 is bigger than 1.5, isn't it? I was checking to see if that's actually, because obviously you can turn this into it's just going to be a sine wave, yeah? Let me actually just write down root 5 over 2 sine of, 2x plus God knows what, yeah? It doesn't matter really, because the important thing is the r value, because that tells you about how high the curve is actually going. We know it's been squished by a factor of 2, yeah, so it's going to have like a double period of sine basically because it's sine 2x, but all I wanted to check was that this line definitely hits it as I thought it would do 4 times. 1, 2, 3, 4. Why is it, why have I done just 2 periods of sine? Because a sine 2x graph squashes it, so there's twice as many peaks in the same range now. So rather than having 1 peak and 1 trough, we've now got 2 peaks and 2 troughs. And then you draw the line minus 1.5 there, and you see you've got 4 solutions. So that's why I went 4 solutions. Yes, there's easier ways, but there we go. Sometimes you just get distracted, don't you, by a method, and you're like, oh, I think this one will work. Okay, so this one, Fort's Thirst, not A, definitely not A. Remember, this is sine of root x, sine of stuff squared. It's definitely bigger than 0. And what's more, you can tell that it's bigger than 1. Sorry, bigger than 1. Did I just say that? You can tell it's trapped between 0 and 1. Sine of stuff, whatever the stuff is, sine of stuff is between -1 and 1. And so sine squared of stuff is between 0 and 1. I do this a lot in my working when I'm doing mathematics. It helps me, clear my mind. But really, I mean, at this point, I was thinking it's not going to be C either, because it's not going to be, a lower peak than a higher peak than a higher peak. This isn't a function which is growing. This is a function which just goes up and down, bounded between 0 and 1. Yeah. So all I had to decide really then was if it was D or B. Well, it has to be B because of this root x. That's a non-linear kind of thing. So you're going to get a massive gap between the peaks. If you like, the first positive peak on sine, the first peak at 1, is obviously when the stuff is root pi over 2. Yeah. In other words, I need root x to be root pi over 2. So I need root x, to equal pi over 2, because then I'll be doing sine of pi over 2 and I'll get a peak. Yeah. Well, that means that x, of course, is pi squared over 4. Yeah, so that first peak occurs at pi squared over 4. Now I'm going to show you why it looks more like that diagram than this diagram. Where's your next peak? Well, your next peak's going to occur. You could take the negative value, it will be the one here, but I'm going to take the positive value. The next peak for sine is like 5 pi over 2. Yeah, because it repeats every 2 pi. Or degree, if you're in degrees, that's cool as well, do it in degrees. This is going to give me 25 pi squared over 4. Oh, pi to the 4, pi squared over 4. And can you see that's a lot further away to the origin than just pi squared over 4? It's 25 times the distance, really, isn't it? And so that must be your 25 pi squared over 4. It just looks more like this graph. Do you see what I mean? It's a non-linear way it's growing. Think about the values that root x could take to give you the peaks, and it should give you that. I like those graph questions actually in the little map short questions. I find they're always nice. I like them. I enjoy them. They're good fun. Okay, this one. I went to the answer very, very quickly, but wanted to sort of justify in my mind here why it was, definitely that. Firstly, this one. Exclude that one because that's going to be a number less than 1. If you've got to put 3 to the power of something, remember, logs find powers. That's what logs do. They find powers. Well, if you've got to put 3 to the power of something to get to 2, it's got to be a number under 1, hasn't it? Because you're going to be like square rooting it, or putting it to the power of 2/3, something like that. As soon as you're doing 3 to the power of a number bigger than 1, the value is bigger than 3, so it can't be that one. Now these, I mean, surely you can see as well, like this kind of thing, like think about roughly where it is, like this, think about 2 squared is 4. Yeah, here we're halfway to 2 squared. Yeah, this is the way I look at it. Here though, well, we're sort of like a third of a way to 4 squared. Yeah, because what I'm saying here is, like, to get from 4 to 16, you've got a gap of 12, and so we've gone up 4, we've gone up like a third of the way. And it's even worse here because you've got to go from like 5 to 25. That's a gap of 20, and like you've gone up like 5 of it, so it's 5 out of 20, so like you're a quarter of the way to 5 squared. And that's why I just knew that it was going to be this one. I suppose, like, that feels a bit like hand wavy to you, maybe. It does sound quite hand wavy the way I'm describing it, but it just seems like we're closer to 2 squared here, like proportionally speaking, than we are here or here. And that's why it has to be this answer. You could do it with mixed base formula. I bet you could do it with mixed base formula, change of base formula. What is a change of base formula again? I prove it occasionally, but log A base B equals log, now how do we do it? How do you change the base? Log C base B over log C base A or something like that. I'm actually going to Google it quickly now. Like, what is the change of base formula? It's something you get. I can't believe I can't remember it. Here we go. Log A of X is log B of X over log B of A. Is that essentially what I've written? I wrote log A of B, so my B is X. Okay, so no, I don't think so. Oh no, hey, yeah, yeah, maybe. Because C doesn't appear here, and I put it there and there, and then did I remember this right in my head? X has gone there and there. That looks right, and then A has gone there and there. Yeah, I think I've got it right. Wow. Well done, me. Okay, so can we do it with a change of base formula? I expect we can, because can't we turn all of them now into the same base? If I want to turn log base 2 of 3, let's do log base 4 of 8 firstly. Can I turn that into log base 2 of 8? Oh, that looks nice. Over log base 2 of 4. Um, and this is going to equal 3 over 2, and that's because 4 to the power 3 over 2 is 8. Yeah, so it's quite amusing me doing that. I've just actually worked out that this actually completely equals 3 over 2. I hadn't noticed that, but yes, it does. I really should have noticed that as well. That is very obvious. So yeah, that's kind of cool. um, I mean, one of the things I'd say here, right, is I think, well, what do I need to make log base 2 be you know like, what do I need to put here to make this equal 3 over 2? And I think it's 2 root 2, yeah, because it's 2 to the 1 1/2, 2 root 2. And 2 root 2, I actually know that as a decimal. So 2 times 1.414 is 2.828, and that's less than 3, yeah? Do you see what I mean? So this has to be a bigger value than 3 over 2, since log is a strictly increasing function. I know I've kind of written off this one down here. Can I change this base? If I've got log base 5 of 10, what can I write as log base 2 of 10, and then over log base 2 of 5? Does this kind of clear this up in many ways? Well, that's 3 and a bit. 3.1, let's say. Let's sort of do it by guesstimates. Let's say 3.2. 2 to the 3.2 is probably roughly 10. And this is going to be like 2.2, isn't it? And 3.2 over 2.2, well, that's definitely less than 3 over 2, isn't it? Well, it's more about, pretty much about the same, actually, to be fair. And so, yeah, this one's going to be higher, isn't it? But yeah, my change of base didn't really show it properly, but I'm going to finish the video now. I'm sure you're probably okay with this one. I hope you can see the argument I'm trying to make there. It's a weird kind of like hand wavy appeal, but it's certainly right. Okay, thanks for listening, and I'll see you later. Bye bye.